Assalamualaikum and hello everyone. We are from RK20 Computer Engineering and we are going to present for Model Control System mini project for our title, which is Automatic Vehicle Control System.
Automatic control vehicle is one of the most promising alternatives for automating many jobs that requires a system without the needs of human interaction. It can be applied in variety of situations and very useful because of the fact that it is automatic and will save us time. It also can reduce the cost of hiring workers. For this project, we implemented the studies of modern control system to develop a system that can be fitted to perform automatic control system that may be useful and benefit others. Software is also used to simulate the equation in this project. We try to ensure that the user of this system can reach their desired expectation. Furthermore, we designed the system to be easier to implement for other applications in future development. Our objectives are to provide solution for the problem, then simulate it in the SCI Lab software to get the board plot and also to calculate the gain and phase margin of the system. To test the automatic control system stability by using transfer function and also to ensure the desired output can be achieved. Next is our aim to evaluate and determine the stability of the system of an automatic control vehicle by using transfer function. To determine the stability of the transfer function by finding the gain and phase margin through the board plot. The board plot, however, can be manually calculated, but sometimes it can give some error due to some mistakes that made by us humans when plotting and draw the graph. Therefore, SCI Lab is used for this task to provide us with some more precise results. To improve the industry in terms of effectiveness, cost, and the use of application.
Hi, my name is Izudin, so I'm going to explain about methodology and the calculation. For the methodology, the system is configured by solving the open loop transfer function of the automatic vehicle system equation. We use software to get the accurate phase and gain margin based on the solved open loop transfer function. So by obtaining the board plot, we analyze the system range and configure it to our desired phase margin compensator lead lag to about 30 degree.
Assalamualaikum and hello. My name is Wan Ahmad Fadli bin Wan Muhammad Azmi. I am from RK20. So I'm gonna present about the system advantage for the automatic control vehicle. Firstly, the system is easier to be implemented as the parts required are widely available worldwide. It means all the parts can be found everywhere and make us easier to construct the system. Moreover, it also can easily add extra feature by adding few components based on the user needs. It also cost efficient and can be used for many applications that need automatic control vehicle in their system. For the example, we can use for transportation of goods and for personal use. Next is system disadvantages. The system may not vary with the surroundings because different pathways and conditions that not well maintained could be dangerous, especially to people's surroundings. The system also cannot recognize other driver reaction and local human driving ethics. It's only follow the program guidance for its work. And then the road rules and regulations from all over the world are not the same. It may require the system to be configured accurately to detect traffic rules from different countries. And that's all the advantages and disadvantages for this system.
Hello, so I'm gonna explain about result and discussion. So we got question number 11, which is driverless vehicle and open loop transfer function, and our system is given by L of S is equal to KV over S over pi plus 1 to the power of 2. So to complete the question, we need to do two tasks, which is the first, draw the bird plot of the system, and secondly, we are need to design a compensator of the system using lead or lag. We are allowed to use Skylab or MATLAB for this project, so we decided to use Skylab. For the first task, we need to draw bird plot, so that to draw the bird plot, we need to have the gain and the phase margin of the system. So given the transfer function, g of s is equal to kv over s over pi plus 1 to the power of 2, and kv is equal to pi. So kg of s is equal to pi over s over pi plus 1 to the power of 2. So we factor out the equation and we get pi multiplied by 1 over s multiplied by 1 over s over pi plus 1 multiplied by 1 over s over pi plus 1. 1 over s over pi plus 1, we got it twice because at the kg of s equation, s over pi plus 1 is power of 2. We factor out it manually because to ease the process of drawing. So to draw a system, we need to find the magnitude and the phase of the system. The magnitude of the system is actually the absolute value of the component. So we took 20 log of the system of bird plot. So we have 20 log of pi plus 20 log of 1 over j omega. Additional 40 log 1 over j omega over pi plus 1 is come because there is 2 1 over j omega. Each one of them will be reduced when any log of 1 over j omega over pi plus 1. Okay, so that's all for the magnitude of the system. And for the phase of the system, the angle of the pi will be plus with the 1 over j omega and 1 over j omega over pi plus 1. So using those value, we can draw our graph or bird plot. We need to find pi as the maximum pi of our system. So P required is given by 30 in the question. So 30 is minus by 21.46 plus 15. So we got at 23.3. The 15 value is required for the safety reason. So we got that the pi max is equal to 20.3.
Hello, my name is Amir Haziq bin Basharuddin, and I will show you the code for the Scilab part, MATLAB. So the first one we show the numerator and denominator, which is from the previous equation, 3.14, and the denominator is this equation. Next, we're gonna use this syslin function, which is we use to find the transfer function, which are 3.14 and over s plus 0.64s plus 0.1s cube. Next, we use this PMGCF function, which is for phase margin. So we can see that we use phase margin TF, which is transfer function that we use above. So the first one down here is GCF, which is gain coherence functions, and which is 0.339789, and phase margin PM, which is 21.716302. This both of these values are in hertz. And the next one we have for gain margin, also for the TF transfer function, we have the gain coherent function, which is 0.5032921, and PM we have 6.18500065. Next we have this we have the body plot, which is the diagram for the code. Before, we have the magnitude, and below it we have phase. So we can see the output of the code that we have been generated by using the body plot, body, and we have to put the transfer function in brackets.
Okay, we know that the current phase is equal to 21.69. The frequency is equal to 0.34 Hz. But we need to find omega of the system. So we need to find in the radian value. So we multiply the 2 pi f equation to get omega c, and after multiply it, we got the value of 2.136 radian per second. In order for us to design a compensator of the system, we need the value of alpha and the value of tau. Okay, so we need to find alpha first. We know that phi max is equal to inverse sine of alpha minus 1 over alpha plus 1. Okay, we already got the value of phi max. So we just substitute the value and solve the equation. So we get the value of alpha is equal to 2.308. Omega m and omega c is actually the same value. Okay, we know that omega c is equal to 1 over tau multiplied by square root of alpha. So we just substitute the value of tau and omega c. Okay, so we get the formula of tau, which is 1 over 2.136 multiplied by square root of 2.308. So we got the value of tau, which is 0.284. So we already got the both two components that we need to draw the compensator. Gc of S is the cohesion of the compensator, which is the part of the compensator. It's equal to 1 plus alpha tau S over 1 plus tau S. This is equation for the lead system. If you have the lag system, alpha location will be in the denominator, not in the numerator. So we just substitute the value that we obtained before. So we get Gc of S is equal to 1 plus 0.66S over 1 plus 0.284S. So the last system will be obtained the last board plot. This is for installing the compensator system in the system. So we need to multiply Gc of S and G of S itself. The display value is already solved to the insert value the display value is already solved to be inserted to the Skylab to get the result.
Next we have the second Scilab code, which also have the numerator and denominator, but the difference is we have the numerator for GCS and denominator for GCS. First we divide both of each S values, then we multiply them to obtain G. Then we use the system function for calculating transfer function, and we get the values for phase margin, which is we have GCF and PM, which is 0.45207.724, and PM 29.096843. Both are in hertz, and we also have for G margin, GCF 0.714402 and PM 7.071139. So on the next, we have this body plot. We can see that we have meet the requirement, which is we need 30 to shift by 30 degrees. So we can say that we have achieved the requirement that we need. Thank you.
In conclusion, lead compensator has its zero closer to the origin than the poles. It can improve the transient response and help to increase error constant up to some extent. It allows to pass higher frequencies and attenuates lower frequencies and increases phase shift. The system should become more commonplace with the passage of time because people are living in a modern network world and constantly has less time on their hands. So by implementing the system, it will help to reduce the time consuming and benefits for every application when it's needed. It also gives you less cost for more production. That's all.